Let me ask you to do something right now. Look at a clock. Any clock. The one on your phone, on your wall, the small one ticking in the corner of your screen. Watch the seconds pass. 1, 2, 3. Each tick is identical. Each interval the same. The clock doesn't hesitate, doesn't rush. It just counts. Steady, reliable, absolute. Now let me ask you a question that sounds almost absurd. Are you sure? Are you sure that second you just watched pass was the same length as the second someone else just watched pass someone driving on the highway, someone flying in a plane, someone orbiting the Earth right now aboard the International Space Station? You'd say yes, of course. A second is a second. Time is time. It flows like a river, carrying us all forward at the same relentless pace, indifferent to who we are or how fast we're moving. That belief, that deeply felt, almost instinctual conviction, is one of the most natural things a human being can hold. It is also, as it turns out, completely wrong. More than a century ago, a 26-year-old patent clerk in Bern, Switzerland, dismantled this belief with nothing more than a pencil, a few sheets of paper, and an imagination unlike any the world had ever seen. His name, of course, was Albert Einstein. And what he proposed in 1905 was not merely a new theory of physics, it was a new theory of reality itself. He told us that time is not a river. It does not flow at a single universal pace. It bends, it stretches, it compresses. It depends quite literally on how you are moving through space. And the key to understanding all it, the thread that stitches together the entire fabric of this revolution, is something you encounter every single morning when you open your eyes. Light. That warm glow that falls across your face when the sun rises, that feeling of comfort, of rightness, of something ancient and elemental touching your skin, it is not merely pleasant. It is a message, a dispatch from the deepest structure of the universe. Because light does not just illuminate the world, it defines the world. It sets the rules by which space and time themselves operate. And once you understand those rules, you will never look at a sunrise the same way again. So let us begin. Let us start where Einstein started, not with complicated mathematics, not with enormous telescopes or particle accelerators, but with a simple, almost childlike question. A question about motion. Imagine you are sitting on a train. The train is moving smoothly at a perfectly constant speed along a perfectly straight track. The blinds are drawn. You cannot see outside. Now here is the question. Can you tell that you are moving? You might say, well, I can feel it. But can you? If the track is perfectly smooth, if there are no bumps, no turns, no acceleration or deceleration, just pure uniform motion, then the coffee in your cup sits perfectly still. A ball placed on the floor does not roll. If you toss a coin into the air, it comes straight back down into your hand, exactly as it would in your living room. Every experiment you could perform inside that sealed train car would give you the same result as if you were standing perfectly still. There is, in fact, no experiment you can do, none whatsoever, that will tell you whether you are moving at 100 kilometers an hour or sitting motionless at a station. This is not a limitation of our senses. It is not a trick. It is a fundamental feature of the universe. Physicists call it the principle of relativity, and it did not originate with Einstein. It goes back at least to Galileo, who noted in the 17th century that a person below the deck of a smoothly sailing ship cannot determine whether the ship is moving or at rest. Einstein took this principle, this old, well-respected idea, and elevated it to the status of a postulate, a foundational axiom of his theory. He declared, the laws of physics are the same for all observers moving at constant velocity relative to one another. No frame of reference is privileged. No one gets to claim they are truly at rest while everyone else is truly moving. Motion is relative. It always has been. Now, if that were all Einstein had said, it would have been elegant but not revolutionary. The revolution came from his second postulate, and this is where things get strange. This is where intuition begins to crack. Einstein declared that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. Let that sink in for a moment because it violates everything your everyday experience tells you about how speeds work. If you are standing on the side of a road and a car passes you at 60 kilometers per hour, you measure its speed as 60. But if you are driving alongside it at 50 kilometers per hour, you measure the car's speed as only 10 the difference between your speed and its. This is simple addition and subtraction of velocities. It works for cars, for baseballs, for sound waves, for everything in your daily life, but not for light. If you are standing still and a beam of light passes you, you measure its speed at approximately 299,792,458 meters per second. Now suppose you climb into a spaceship and chase after that beam of light at half the speed of light at 150,000 kilometers per second. Intuition says you should now measure the light beam as moving away from you at only half its original speed. But you don't. You measure it at the full 299,790,725 meters per second. Exactly the same. Now suppose you turn your spaceship around and fly toward the light source at half the speed of light. Intuition says the light should now appear to approach you at 1.5 times its usual speed. But it doesn't. You measure it at 299,792,458 meters per second. Always. No matter what. The speed of light is not relative. It is absolute. It is the one thing in the universe that does not care how fast you are going. This is, to put it gently, profoundly weird. And when Einstein first proposed it, many physicists found it difficult to accept. But he did not pluck this idea from thin air. There was evidence, disturbing, beautiful, undeniable evidence. In 1887, two American physicists, Albert Michelson and Edward Morley, conducted what is now regarded as one of the most important experiments in the history of science. At the time, physicists believed that light, like sound, needed a medium to travel through. Sound moves through air. Ocean waves move through water. So light, they reasoned, must through water. So light, they reasoned, must move through something too. They called this hypothetical substance the luminiferous aether, a mysterious invisible substance that permeated all of space, providing the backdrop against which light waves rippled. If the ether existed, then the Earth, as it orbited the Sun at roughly 30 kilometers per second, should be plowing through it like a boat through still water. And just as a boat creates different wave patterns in front of and behind itself, the Earth's motion through the ether should affect the speed of light, depending on the direction you measured it. Light traveling in the same direction as the Earth's motion should appear slightly slower. Light traveling perpendicular to it should appear slightly faster. The difference would be tiny, but Michelson had built an instrument exquisite enough to detect it, his interferometer, a device that split a beam of light into two perpendicular paths, bounced them off mirrors, and recombined them. If the two beams traveled at even slightly different speeds, the recombined light would produce a telltale interference pattern, a set of shifting fringes that would betray the Earth's motion through the ether. They ran the experiment. They rotated the apparatus. They tested it at different times of day, different times of year, in different orientations. And they found nothing. No shift. No difference. No matter which direction they sent the light, it always traveled at exactly the same speed. The ether, it seemed, did not exist. Or if it did, the universe was conspiring in some extraordinary way to hide it. This null result baffled the physics community for nearly 2 decades. Various physicists proposed increasingly elaborate explanations. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently suggested that objects moving through the ether physically contracted in the direction of their motion, that rulers literally shrank in just the right way to mask the expected difference. It was a clever idea, but it felt like a patch, a mathematical band-aid on a deeper wound. Einstein's genius was to stop patching and start rethinking. He didn't try to explain why the Michelson-Morley experiment gave a null result within the old framework. He asked what kind of universe would naturally produce that result. And the answer was a universe in which the speed of light truly is constant for all observers. Not because of some conspiracy of contracting rulers and slowing clocks, but because that is simply how reality works. The speed of light is woven into the fabric of existence itself. It is not just the speed at which light happens to travel. It is the speed at which causality propagates, the ultimate speed limit of information, of influence, of connection. It is, in a very real sense, the speed of reality. But if you truly accept that the speed of light is the same for everyone, then you are forced into a series of conclusions that will shake your understanding of time to its foundations. Because speed is distance divided by time. And if speed is constant while distance and the observer's motion are not, then something else must give. That something is time itself. Let me show you what I mean. And to do so, let me introduce you to one of the most beautiful thought experiments in all of physics. It is called the light clock. Imagine a clock that works in the simplest possible way. It consists of two mirrors, one above the other, separated by a fixed distance. A single photon, a particle of light, bounces back and forth between these two mirrors. Every time the photon completes one round trip from the bottom mirror to the top and back again, the clock registers one tick. This is our light clock. It is the purest timekeeper imaginable because its mechanism is light itself and we know exactly how fast light travels. Now place this light clock on a spaceship, oriented vertically so the photon bounces straight up and down. If the spaceship is at rest or moving at constant velocity, which as we have established is physically equivalent, the photon travels a simple, straight path, up, down, up, down. Each tick takes the same amount of time. The passengers on the spaceship see a perfectly normal clock. But now let us watch this same clock from outside the spaceship from a space station, say, as the spaceship glides past at a significant fraction of the speed of light. What do we see? We see the same photon bouncing between the same two mirrors. But now the spaceship is moving. So in the time it takes the photon to travel from the bottom mirror to the top mirror has moved sideways. The photon, from our perspective, has not traveled straight up. It has traveled diagonally along a longer path. And since the photon must still travel at the speed of light, because the speed of light is the same for all observers, it takes longer to complete this diagonal journey than it would to travel straight up and down. The tick of the light clock, as we observe it from outside, takes longer. The clock is running slow. Think about what this means. It is not that the clock is malfunctioning. It is not that the mechanism is being affected by the motion in some physical way. Like a pendulum being jostled. The light clock is the simplest possible clock. Its mechanism is the speed of light itself. If this clock runs slow, then time itself is running slow. Time on that moving spaceship is genuinely passing more slowly than time for us on this space station. And before you object, before you say, well, this is just some trick of optics, some artifact of how we observe the light, consider this, everything on that spaceship is affected. Not just the light clock. Every atomic clock, every biological process, every heartbeat, every thought in the minds of the passengers. If they are eating breakfast, their toast takes longer to brown. If they are watching a movie, the movie runs slower. If they are aging more slowly. Not in some metaphorical sense. Literally. Measurably. If the spaceship flew at high speed for what the passengers experienced as 1 year and then returned to the space station, the people on the station might have aged 10 years or 100, depending on how fast the ship traveled. The passengers would step off the ship, genuinely younger than the contemporaries, having lived fewer seconds, fewer heartbeats, fewer moments. This is time dilation, and it is not science fiction. It is one of the most thoroughly confirmed predictions in all of physics. Now you might wonder, doesn't this create a contradiction? If motion is relative, then from the spaceship's perspective, it is the space station that is moving. So shouldn't the people on the space station be the ones whose time is running slow? And the answer is yes. From the spaceship's perspective, the station's clocks are running slow. Each observer sees the other's time as dilated. This seems paradoxical and it troubled physicists for years. But the paradox dissolves when you realize that comparing clocks requires bringing them back together, which requires acceleration, which breaks the symmetry. The twin who travels and returns has changed frames of reference. The twin who stayed has not. And it is the traveling twin who will always be younger. At everyday speeds, driving a car, flying in a plane, the effect is almost inconceivably small. A pilot who has spent an entire career in the air, accumulating tens of thousands of flight hours, has aged perhaps a few microseconds less than someone who stayed on the ground. You will never notice it. You will never feel it. But it is there. It is real. And it becomes dramatic as you approach the speed of light. At 90% of the speed of light, time on the moving ship passes at less than half the rate of time for a stationary observer. At 99%, a factor of about 7. At 99.99%, a factor of over 70. Time dilation is not a gentle slope. It is a cliff. And at the speed of light itself, time stops altogether. A photon. From its own perspective, if a photon could have a perspective experiences no time at all. It is emitted and absorbed in the same instant, even if from our perspective it has traveled across the entire observable universe for billions of years. Think about that the next time you step into the morning sun. The photons landing on your skin are, from their own frame of reference, ageless. They have not experienced a single moment of time since they were born in a nuclear furnace of the sun's core. For them, creation and arrival are the same event. They are, in a manner of speaking, still being born at the very instant they warm your face. But time dilation is only the beginning. Because once you accept that time is relative, that it depends on how you are moving, you are forced to confront an even more unsettling consequence. Something that strikes at the very heart of what we mean by now. Let me set up the scene. Imagine a train, a very long train moving at a significant fraction of the speed of light. In the exact center of the train, someone sets off a flash of light. The light radiates outward in all directions, traveling toward the front of the train and the back of the train simultaneously. Now, from the perspective of someone riding on the train, the light has the same distance to travel in both directions. The front of the train is just as far from the center as the back. And since light travels at the same speed in all directions, the light reaches the front wall and the back wall at exactly the same time. Two simultaneous events. The flash arrives at the front. The flash arrives at the back. But now consider this same situation from the perspective of someone standing on the platform watching the train rush past. From their vantage point, the train is moving forward. So after the flash is emitted, the back wall of the train is moving toward the expanding light, while the front wall is moving away from it. The light still travels at the same speed in both directions. This is Einstein's postulate. Remember, it does not change, but the back wall has moved closer, so the light reaches it first. The front wall has moved farther away, so the light reaches it later. The two events that were simultaneous on the train are not simultaneous on the platform. The platform observer sees the flash reach the back of the train before it reaches the front. This is the relativity of simultaneity, and it is not an illusion. It is not a matter of delayed signals or slow information processing. It is a fundamental feature of space-time. Two events that are simultaneous in one frame of reference are genuinely not simultaneous in another. There is no absolute universal now that stretches across the cosmos like a razor-thin sheet, dividing the past from the future. What counts as now depends on how you are moving. Take a moment to appreciate how radical this is. Since the time of Newton, since the time of common sense, we have divided the universe into three clean categories. The past, which has already happened, the future, which has not yet happened, and the present, the infinitely thin boundary between them. Everyone, we assumed, shares the same present. When you say right now, you imagine that right now is the same for your friend across the room, for an astronaut on Mars, for a being in a distant galaxy. But Einstein showed that this is not the case. Your now and the astronaut's now do not necessarily agree, especially if you are in motion relative to each other. Events that lie in your present may lie in the astronaut's past or their future. The neat division between past, present, and future is not a feature of the universe. It is a feature of your particular frame of reference. And different frames carve up the universe differently. This does not mean that causality breaks down. The order of cause and effect is preserved for any two events that could influence each other. That is, events close enough in space and time that a signal traveling at or below the speed of light could connect them. But for events that are far apart in space events, separated by what physicists call a space-like interval, the order in which they occur can depend on the observer. One observer's before is another observer's after. The universe does not keep a single universal ledger of when things happen. It keeps many, one for each possible state of motion, and they do not always agree. If this makes you uncomfortable, you are in good company. It made many physicists uncomfortable too. But the evidence is overwhelming. Let us turn then from thought experiments to reality. Because one of the most remarkable things about Einstein's theory is that it is not merely beautiful mathematics. It is confirmed by the world we live in, every single day, in ways both exotic and mundane. Consider, first, something mundane, the global positioning system. Your phone's ability to pinpoint your location to within a few meters depends on a constellation of satellites orbiting the Earth at an altitude of about 20,200 kilometers. Each satellite carries an extremely precise atomic clock, and the system works by comparing the time signals from multiple satellites to calculate your position. But those satellites are moving at about 14,000 kilometers per hour relative to the ground, and special relativity tells us that their clock should tick slightly slower because of that motion, about 7 microseconds per day slower. Meanwhile, general relativity, Einstein's later, even more profound theory, which extends these ideas to include gravity, tells us that the clocks should tick slightly faster because they are farther from the Earth's gravitational field by about 45 microseconds per day. The net effect is that the satellite clocks gain about 38 microseconds per day relative to clocks on the ground. 38 microseconds. It sounds negligible. But light travels about 11 kilometers in 38 microseconds. If the GPS system did not account for relativistic time dilation, both special and general, your position would drift by roughly 11 kilometers every single day. Within a week, the system would be useless. Every time you use GPS to navigate to a restaurant, to find a friend, to land an airplane, you are relying on Einstein's theory of relativity. It is not abstract. It is not philosophical. It is embedded in the infrastructure of modern civilization. Now consider something exotic. Muons. A muon is an elementary particle, similar to an electron but about 200 times heavier. Muons are created in abundance when cosmic rays, high-energy particles from deep space slam into the upper atmosphere at altitudes of about 15 kilometers. The trouble is that muons are unstable. They decay with a half-life of about 1.5 microseconds. If you do the math without relativity, even if a muon were traveling at the speed of light, it could only travel about 450 meters before decaying. So, most muons created in the upper atmosphere should decay long before reaching the ground. They should be rare at sea level. But they are not rare. We detect enormous numbers of muons at the Earth's surface. They arrive in quantities that would be completely inexplicable without time dilation, because those muons are traveling at roughly 99.8% of the speed of light, and at that speed, their internal clocks are running slow relative to ours. Their 1.5 microsecond half-life, from our perspective, is stretched to about 30 microseconds. And in 30 microseconds at that speed, they can travel about 9 kilometers. That is enough. The muons survive the journey not because they are special, not because they are immune to decay, but because time itself is passing more slowly for them. From the muon's own frame of reference, the explanation is different but equally valid. The muon's internal clock ticks normally, but the distance from the upper atmosphere to the ground is compressed by the same relativistic factor. The 15-kilometer journey becomes a journey of only a few hundred meters, easily survivable within its short lifetime. Two different frames of reference, two different explanations, one universe. Both descriptions are equally true. Neither is more real than the other. This is the strange democracy of relativity. Every observer's perspective is equally valid, and the universe maintains perfect consistency despite allowing radically different descriptions of the same events. Muons, then, are tiny messengers from the sky, carrying evidence of time dilation in their very existence. Every time one strikes a detector at the Earth's surface, it is a small, silent confirmation that Einstein was right. That time is not what we thought it was, but we are not yet finished. Because there is a deeper layer to this story, a unification that takes everything we have discussed, time dilation, length contraction, the relativity of simultaneity, and folds it into a single breathtaking geometric picture. And for this, we must turn not to Einstein himself, but to his former mathematics professor, a man named Hermann Minkowski. In 1908, 3 years after Einstein published his special theory of relativity, Minkowski gave a lecture that began with one of the most dramatic opening lines in the history of science. He said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." What Minkowski realized was that the strange effects of special relativity, the stretching of space, the disagreement about simultaneity, are not separate, unrelated phenomena. They are all manifestations of a single underlying reality. Space and time are not separate things. They are woven together into a single four-dimensional fabric that Minkowski called space-time. You are familiar with 3 dimensions of space: left, right, forward, backward, up, down. You can point in any direction, and it can be described as a combination of these 3. Now add a 4th dimension, time. Not as something separate from space, not as a river that flows alongside the spatial world, but as a genuine geometric dimension, intertwined with the other 3 in the same way they are intertwined with the other 3 in the same way they are intertwined with each other. This is not merely a mathematical convenience. It is a description of reality, and it comes with a startling insight about motion. You are, right now, moving through space-time. Even if you are sitting perfectly still in your chair reading this, moving through zero space, you are still moving through time. You are hurtling into the future at the rate of 1 second per second. In Minkowski's framework, this can be made precise. Every object in the universe moves through space-time at a fixed, constant speed, and that speed is the speed of light. Let me say that again, because it deserves to be heard clearly. You are right now moving through space-time at the speed of light, not through space. Through space-time. The total magnitude of your space-time velocity or speed through the four-dimensional fabric is always exactly the speed of light, roughly 300,000 kilometers per second. But here is the crucial subtlety, that total speed is divided between your motion through space and your motion through time. If you are sitting still, all of your space-time speed is directed through time. You are moving through time as fast as possible. But if you start moving through space, if you stand up and walk, if you get in a car, if you board a rocket, some of your space-time speed is redirected from the time direction into the space direction. And since the total must remain constant, your speed through time decreases. This is time dilation, re-expressed in the language of geometry. It is not some strange, inexplicable phenomenon. It is a rotation in space-time. Just as turning your car to the right redirects some of your forward velocity into sideways, velocity reducing your forward progress moving through space redirects some of your temporal velocity into spatial velocity, reducing your progress through time. And now the cosmic speed limit makes perfect intuitive sense. You cannot travel faster than the speed of light through space because you cannot redirect more than all of your space-time speed into the spatial direction. If you somehow managed to travel through space at exactly the speed of light, you would have no speed left over for time. Time, for you, would stop. You would not age, you would not change, you would not experience duration. This is precisely the situation of a photon. Light moves through space at the speed of light, and therefore it does not move through time at all. A photon does not experience time. It cannot. It has used up its entire budget of space-time speed on spatial motion. There is something almost unbearably elegant about this. The speed of light is not just a speed limit. It is the universal rate of motion through space-time, the one quantity that all objects share, the heartbeat of the cosmos. And the interplay between space and time, the way they trade off, the way moving faster through one means moving slower through the other, is not a quirk or a complication. It is the geometry of reality. Consider what this means for the morning sunlight on your face. Those photons left the sun about 8 minutes ago from your perspective. They crossed 150 million kilometers of space. But from their own perspective, as we discussed, they experienced no time at all. Their entire budget of space-time velocity was spent on motion through space. They moved through time not one instant. For them, the sun's surface and your skin are the same place at the same time, connected by a path of zero duration. They are, in Minkowski's geometric language, separated by what is called a null interval, zero space-time distance. You are, in a sense, touching the sun, not metaphorically, geometrically. In the four-dimensional fabric of space-time, the point where that photon was emitted and the point where it strikes your cheek are connected by a path of zero lengths. Light does not merely travel between things. It connects them, in the deepest geometric sense, across what we perceive as vast gulfs of space. This is why light is so central to the theory of relativity. It is not simply that Einstein happened to be interested in optics. It is that light occupies a unique and privileged position in the structure of space-time. It sits on the boundary. It is the knife edge between the spatial and the temporal, the entity that uses all of its space-time motion for space and none for time. It defines the geometry. It draws the borders of cause and effect. The paths that light can follow through space-time, the light cones, as physicists call them, determine which events can influence which other events, which things can be causes, and which can be effects, what the words before and after even mean. When you watch a sunrise, you are not merely witnessing a pretty astronomical phenomenon. You are watching causality itself make contact with you. You are watching the boundary condition of reality, the speed of light, the structure of space-time deliver energy from a thermonuclear furnace across 150 million kilometers of vacuum, and it arrives in its own frame of reference instantaneously. From the photon's point of view, the fusion reaction that created it and the retinal cell that absorbs it are the same event. And this brings us at last to the question in our title: why does morning sunlight feel so good? There is, of course, a biological answer. Sunlight stimulates the production of serotonin, suppresses melatonin, regulates your circadian rhythm, triggers the synthesis of vitamin D in your skin. These are all real, measurable, important effects. But I want to suggest that there is something deeper at work, something our bodies understand, even if our conscious minds do not. We are creatures of space-time. Every atom in your body was forged in a star. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it, was cooked in the nuclear furnaces of ancient suns that lived and died billions of years before our solar system formed. You are quite literally made of starlight, and when the morning sun touches your face, there is a sense in which you are being reunited with the process that made you. The photons carry information not in any encoded symbolic sense, but in the most fundamental physical sense. They carry energy. They carry momentum. They carry the signature of the nuclear reactions that produce them. And they arrive along the null geodesics of space-time, the straightest possible paths through the four-dimensional fabric of reality, traveling at the one speed that the universe itself is built around. Perhaps what we feel in that warm glow of morning light is a resonance, a recognition, an echo of the deep connection between matter and light that has shaped the universe since its earliest moments. The Big Bang itself was an event of unimaginable luminosity. The cosmic microwave background, the oldest light in the universe, emitted when the cosmos was only 380,000 years old, still bathes us from every direction, though it is cooled to just a few degrees above absolute zero. We swim in ancient light. We are immersed in it. And every morning, our nearest star sends us a fresh reminder of the relationship between energy and matter, between space and time, between the observer and the observed. Einstein showed us that these are not separate categories. Space and time are one. Energy and matter are one. That is the meaning of his most famous equation, E equals mc squared, which tells us that mass is simply concentrated energy, and energy is liberated mass, and the conversion factor between them is, once again, the speed of light squared. Light is the thread that runs through everything. It is the constant in a universe of variables. It is the one speed that all observers agree upon, the one quantity that does not depend on your frame of reference, the metronome of space-time, the heartbeat of the cosmos. When you stand in the morning light, you stand at the intersection of all these ideas. The photons warming your skin have traveled through space-time at the universal speed, experiencing no time of their own. They connect you to a star whose gravity warps the space-time around it, bending the paths of those very photons, a further consequence of Einstein's general relativity, which extends special relativity to include acceleration and gravity and the curvature of space-time itself. The clock on your wall is ticking at a rate determined by your position in the Earth's gravitational field and your velocity relative to the distant stars. The now that you experience this moment, this breath, this heartbeat is not a cosmic universal. It is yours. It is defined by your particular path through space-time, your particular world line, as Minkowski would say. And yet it feels universal. It feels absolute. The morning sun rises, and it feels like the most fixed, most certain, most timeless thing in the world. That is the great irony of relativity. It reveals that nearly everything we took to be absolute time, simultaneity, the length of a ruler, the duration of a heartbeat, is relative, dependent on the observer. And the one thing we might have thought was relative the speed of light, which surely should depend on how fast you chase it, turns out to be the one absolute. The universe is built on a foundation of light, and that foundation does not shift. There is a passage from Einstein's writings that I think about often. Late in life, after the death of his close friend, Michele Besso, Einstein wrote a letter to Besso's family. He said, "Now he has departed from this strange world a little ahead of me. That signifies nothing." For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. This was not a throwaway consolation. Einstein meant it quite literally. In the block universe of Minkowski spacetime, all of time exists in the same way that all of space exists. The year 1905 is no less real than the year 2026. They are simply different locations in the four-dimensional fabric. We experience time as flowing, as moving, as carrying us forward. But that experience, however vivid, is not reflected in the equations. The equations show a static, four-dimensional block in which all events, past, present, and future, simply are. Your birth, your death, and every moment in between are all equally real, all equally present in the fabric of space-time, like frames in a film strip that exists all at once, even though the projector shows them one by one. Whether or not you find this comforting, whether the block universe feels liberating or claustrophobic, whether the idea that all moments exist eternally gives you peace or vertigo, is a deeply personal question and one that physics alone cannot answer. But it is, at the very least, awe-inspiring. The morning light on your face is not a fleeting, vanishing thing. In the geometry of space-time, it is eternal. That photon's path from the sun to your cheek is a fixed line in the four-dimensional fabric, as permanent as a line drawn in stone. The warmth you feel is not disappearing into the past. It is always there, at that particular coordinate in space-time, forever. And perhaps that is the deepest reason why morning sunlight feels so good. Not just because of serotonin, not just because of circadian rhythms, but because at some level beneath conscious thought, beneath language, beneath all our categories and concepts, we recognize what it is. It is the fundamental constant of the universe, arriving on schedule, connecting us to the heart of a star, reminding us that we are not separate from the cosmos. We are expressions of it. We are space-time looking at itself, warmed by its own light. So tomorrow morning, when the sun rises, step outside. Feel the light on your skin. And know that what you are feeling is not simple. It is not ordinary. It is the speed of the universe arriving at your doorstep. It is a message written in the only language the cosmos truly speaks, the language of light, of space-time, of the deep, strange, beautiful geometry that Einstein and Minkowski uncovered more than a century ago. A second passes on your clock. But it is not the same second that passes on the clock of a cosmonaut overhead, or a muon screaming through the atmosphere, or a photon that has never experienced a second at all. The universe does not have one time, it has many. And they are all real. And they are all woven together by light, the golden thread that holds the fabric taut. Look at the clock again, watch it tick, and this time, know what you are really seeing. Not the passage of some universal absolute time, but a single local heartbeat, your clock, your path through the four-dimensional tapestry of existence. It is unique, it is yours, and it is made of the same stuff as starlight.